Hello, amazing students. The goal of this video is such that you can create from a full molecular chemical reaction, what we've been creating since mid-year. Well, from that, can we more display what really we have in our beaker? Can we create the ionic and then the net ionic equation? So at the end of the video, this is what we'll be able to do. Again, for our little mini unit, our goal is to really understand what is inside of a solution. What is the exact particle nature? Okay, well, let's just review some terminology that we learned in our first lesson. How do we know and judge if a given formula is soluble? And then if we have water present, it will get the AQ phase symbol, or insoluble. So it doesn't dissolve in water and we'll get the solid phase symbol. Well, remember, as honor students, you do not have to memorize the solubility rules. We need to just know how to apply the given information, either in the table, in this kind of sentence format that is in your chapter, or from this more kind of streamlined table. So I would only provide you compounds that we could check here. So we want to check the cation and anion composition. Remember, if your substance includes these, they'll be soluble, but we need to check the exceptions that when paired make them insoluble. And then here are the mainly insoluble, but we need to check the exceptions that would, when bonded, would make them soluble. We'll keep practicing, but just have this nice and handy. We apply the solubility rules to know these. Remember, ionic compounds, if they are soluble, when placed into water, they break up into the cations and anions that make up the ionic compound. Then these solvated ions, or ions that are surrounded by water molecules, will be free moving, making it an electrolyte. So free moving ions. And we know soluble ionic solutes in water create the free moving ions that then will light up the light bulb and act as an electrolyte, as we saw in class. If there are no free moving ions and the light bulb doesn't light up, well, then it's a non-electrolyte. And so the grand majority of covalent substances that are polar and do dissolve in water, they do not dissociate. But we do have a small category of covalent compounds, acids that ionize. And that is an acid being an acid and donating the hydrogen ion to water. Remember, we have strong acids and we have weak acids. And strong acids, those are those 6 that we talked about. They, for example, HI, when react with water, perform a reaction that makes what then are free moving ions, and all of the acid that can will create as much of these ions as possible. So they're going to be electrolytes. They're creating free moving ions, and they're going to create a good number of them. So they are considered strong electrolytes, where weak acids like vinegar, that is a just great example. Well, it still is an acid. It creates some hydronium, but not very much. The overwhelming majority remains as this molecule and the acetate ion in this case. So we still create that hydronium ion, but just not very much. So only 1 to 3% of what we put in solution that's a weak acid creates our ions. So these are weak electrolytes. Okay, well, let's dig in our first example and start with an actual full chemical equation. So if we were given this reaction to start, well, that is the full balanced chemical equation. And sometimes you do start with that. So this is the full equation, sometimes known as the molecular equation, even though we don't have molecules there. Well, next is the ionic equation. And the ionic equation shows any species that is existing as an ion. Well, what can be existing as an ion? Those things that dissociate and ionize. So soluble ionic in solution. So when we see that NaCl, AQ, when we see that Al, NO3, 3, AQ, they're going to be broken up into ions. What else? Strong acids when they're dissolved in water, only strong. So those 6 we will write as full separate ions. H2SO4, HNO3, HClO4. Everything else is either not going to create ions or will be insoluble or existing as a molecule. So let's dig in and look at some examples. So here, ionic, soluble, ionic because metal and non-metal. So I will break this into the ions that make it up. The ions here are the calcium +2. They are dissolved in water. So I get the phase symbol of AQ. And chloride. There are 2 chlorides for every 1 calcium. Okay, that is in contact, because I'm assuming I add these to the same beaker, with silver nitrate. All nitrate compounds are soluble. It's in solution. Metal cation and non-metal anion. So I break this into the silver and the nitrate ion. So just like we together in class said, okay, whenever we dissolve this soluble ionic in water, it will dissociate. You create separate silver from the nitrate ion. Remember we did that? Well, that's just what we're doing here. What we also need to respect is the ratio of ions, not only within the formula, 1 silver ion for every one nitrate ion, but also per the balanced equation. So 1 nitrate comes from this and 1 silver ion, but I needed 2 moles of it to balance and respect the law of conservation of mass. So that 2 is written here and is written there. Okay, so whenever I mix these are my reactants. Okay. Next, okay, we're forming calcium nitrate. All nitrate compounds are soluble. So this will be separate calcium. I have 1 mole of calcium nitrate that gives me 1 mole of calcium +2 and 2 moles of nitrate. All right, then what do I have next but neutral, insoluble silver chloride? This is not existing as separate ions. Okay, this is the ionic. It shows anything that is existing as an ion, Oh, I forgot that phase symbol. All right. Then the net ionic equation. The net ionic equation is really what we are after. The net ionic shows what is being chemically transformed. If we look and compare the reactant to the product side, I have the calcium +2 ion, one of them. It's aqueous. Well, on the product side, calcium +2 aqueous, not changing in number or the way we are writing the form of it. It begins the calcium +2 ion surrounded by water molecules and remains that way. Is there anything else that is the same chemically on the left and the right? Nitrate. Now, my chloride does get transformed. Here, I have two separate chloride ions dissolved with water. I don't have two separate. They are bound with silver and no longer free and moving. And the same with the silver. Calcium and, oh, I didn't mean to circle chloride, very sorry. The calcium and the nitrate, those are called spectator ions, named so appropriately. They're just there to watch. They're surrounding the action, but they aren't involved in the action. What is chemically transformed is the two chlorides. When they meet the two silver ions, we make two silver chloride insoluble solid particles. So the net ionic equation is free of spectator ions. We would write two chloride, and it doesn't matter the order, just as long as these are both on the reactant side, to make two silver chloride insoluble solid. Now, I must say, we know that we want these to be in the lowest whole number ratio. So these all would reduce to a coefficient of 1. But this is really what us and as chemists are concerned with. What actually is undergoing a chemical transformation. So that is the net ionic, free of any spectators. So we began with this double replacement reaction, but we eliminated spectator ions to really show that it's the creation of a precipitate that drives this reaction. Okay, let's look at another example. Now, if you were asked to create the ionic and the net ionic, all right, well, compound plus compound, I'd say double replacement. Let's switch our cations. So we'll have HOH, which you can absolutely write as water if you would rather. And MgCl. Now we know +1 - 2, that's our formula, +2 - 1, so MgCl2. All right. Balancing. We are going to need a 2 there. And a 2 here. All right. Now, is a driving force being satisfied? Is a driving force being satisfied? This will not have any motivation to put in the work to break bonds if a driving force is not being satisfied. Remember, our driving forces are creation of water, yay, driving force, production of a gas, so not making O2, not making CO2, not making H2 here, creating a precipitate like we did in the last example, or transferring electrons, which we have yet to talk about. All right, so yeah, we are fulfilling a driving force. Now, what phase symbol? Liquid. Water isn't dissolved in water. Now, magnesium chloride, applying solubility rules. Magnesium is not one of our categories. Chloride, usually soluble, and magnesium +2 is not an exception that would make it insoluble. So being soluble, we put an AQ. Okay, so ionic next. All right. So what exists as separate ions? Well, soluble ionic. So this will be dissociated. Soluble ionic, dissociated. Water, no, it's not soluble ionic, and it is not a strong acid. Strong acid. So now we know that HCl is reacting with water to create hydronium and chloride. But we have a little shortcut. Instead of writing hydronium, we just write the hydrogen ion, realizing that really is H3O+, but to save some room, some space, and graphite. And then chloride. But looking at my balance equation, I need a 2 and a 2. That will be combined with, I only have 1 mole of these that will give me magnesium, but 2 hydroxides. All right. But this doesn't exist as separate ions, but this does. Okay, my spectators, chloride does not undergo a transformation and the magnesium ion does not. So the net ionic would be 2 hydrogen ions when they find 2 hydroxides, and we are making 2 water molecules. I can't believe that we need to reduce these just like the previous example, but we'll have the hydrogen ion plus hydroxide yielding water. That's our driving force. Okay, I am asking that we complete number 2 and 3 on page 7. Reason why I did want to assign number 1 is because I want to do that with you. So the problem is asking, will we get a precipitate if lithium sulfate, all right, so lithium sulfate, sulfate's -2, lithium is +1, so Li2SO4. Now, do you see it's solutions? So we're already being told, oh, that's soluble. And barium nitrate, a solution, barium is +2, nitrate is -1, so BaNO3 2 are combined. Will a precipitate form? Well, double replacement. So my lithium will be with nitrate, +1, -1, and my barium will be with sulfate. It doesn't matter the order that you wrote those, +2, -2. To balance the equation, I need a 2 here. All right, will we form a precipitate? So we need to look at our solubility rules. All right. Well, all nitrates are soluble, no exception. So that gets a big AQ. All right, sulfates. Oh, they are usually soluble, but I need to check an exception. Barium is. There's my precipitate. So we did get one. Yeah. So barium sulfate's my precipitate. So if so, identify the spectator ions and write the net ionic. To get the net ionic, I think we probably need the ionic. So I don't have any strong acids here or any covalent, just ionic. And I know soluble ionic will exist as ions, exist as ions, exist as ions, but not that. So for the balanced, I get 2 lithiums for every 1 sulfate. You need to have ion charges and phase symbols. Barium +2 and 2 nitrates. We are creating 2 lithiums and 2 nitrates, but this will not be dissociated. All right, my spectator ions, I'm going to circle them. So 2 lithium plus 1 and 2 nitrates. So my net ionic is sulfate plus barium, yielding barium sulfate. Okay, so have we done enough that you can give this a try? So what I'm asking us to do, please, is number 2 and number 3, as well as number 2 on page 8 in our packet, and that's applying solubility rules. And then on page 9, number 17. Please feel free to send questions my way through email. I'll look forward to seeing you guys next time in class.